Hi, and welcome to another Hopper on 6502 video. This video is about Hopper Basic, which is a basic I wrote specifically for the Hopper 6502 single board computer. The single board computer typically has 32K of ROM and 32K of RAM. So I gave myself that as one of the objectives is, how much can I fit into 32K, right? And part of it is I wanted it to be self-hosted. So you don't need anything other than a serial terminal and the binary. So you take the binary and you burn it onto your EEPROM, and you take any old serial terminal on any computer, don't care if it's Linux or Windows, and as long as you configure it correctly, you connect to the machine. And if I hit the reset button, the little red button, let's go back to that. Hit the little reset button. We get a fresh start there, right? So one of the features that I wanted to have was a file system. So this file system is sitting on this tiny little 8-pin EEPROM here, the EEPROM. So it's an I2C little EEPROM, and you'll be surprised how old I2C is. It dates back to late 70s, early 80s. I think it was Philips. Anyhow, it has a file system, a full file system in it. And I also wasn't just going to build a basic that's like every other basic. I wanted to build a modern basic. So by that I mean it's been almost 50 years since the original classic basics, and we've learned a few things about programming since then. So how's about we try and build a modern basic to run on the classic machines. The other thing I wanted to do, like I said, I wanted to be self-hosted so that you can write your programs right on the device like that. And I also wanted it to be blindingly fast. So to be fast, it's not an interpreter, it's a compiler, complete with a full optimizer, like a peephole optimizer, and a blindingly fast virtual machine running bytecodes. So how fast is it? So if we run Noel's RetroLab benchmark, you can see here by the correct answer that it's using 32-bit integers. It only has one numeric type, a 32-bit integer, and it's taking half a second to perform this benchmark. And my clock speed is 8 megahertz. So if this was running at 1 megahertz, that would be 8 times, it would be 4 seconds, right? So for some perspective, where does that fit into the greater picture in terms of Noel's benchmark tables, right? So this number is seconds here, and we took half a second. So the fastest thing here takes 1 second. And there are machines here that are running at 28 megahertz and 18 megahertz, and we're running at 8 megahertz. But let's just say we're running at 1 megahertz. So we take 4 seconds. What is it? 8 times. Let's go back and have a look. So 8 times that, 4 seconds. So on a 1 megahertz machine, we'd take 4 seconds. So that would put us still up here somewhere, right? So faster than BBC Basic by quite a stretch. Faster than things like a ZX Spectrum. All these machines. And the hilarious one is it would be faster than, Gates William Basic on IBM PC clones in, this is a 16-bit chip running at almost 5 megahertz, and we are, what's that, 8 times faster than that? On a 1 megahertz machine, on an 8 megahertz machine, on a 4 megahertz machine, we would be running at 2 seconds, so we would be 15 times as fast as an IBM PC. So I believe that counts as having made it fast. There's other benchmarks we can look at as well. There's the classic. Let me just stop it quickly and list it. So if I do Control C for break, it shows me where in the program I broke, and it does syntax errors and runtime errors the same way. So if I had division by 0, it would show me where in the code as well. So this is the classic byte magazine benchmark, prime number sieve, and I'm going to run it, and I'll pause the video because it does take a little while, and then we'll see where it lines up with the benchmarks of the classics. So let's run that. So it does 10 iterations of the benchmark to get an average. And that kind of works in our favor because the first iteration for us is slightly slower than the subsequent iterations because the compiler has to compile on the first one, and on the subsequent ones it doesn't. Anyway, I'm going to pause the video. All right, we're getting there. We're close to done. There we go. 53 seconds. Again, we're running at 8 megahertz. So if we were running at 1 megahertz, let's call it 420 seconds, right? So let's say 420 seconds because 8 megahertz 6502s didn't exist in 1981 when the Byte Magazine benchmarks came out. So I've brought up the Byte Magazine benchmarks on the screen behind here. So we're at 53. What did we say? 420 seconds or something. 420 seconds. So 8 times as much as that. And 420 puts us somewhere over here. So AppleSoft is actually Microsoft Basic. No, it's a Basic from Microsoft on the Apple. So they're 7 times as slow as us, whereas Integer Basic from Wozniak's Basic, 5 times, 4 or 5 times slower than us. And these are 16-bit integers. This was floating point, but these are 16-bit integers, and we're 32-bit integers, and we're still running, blindingly fast. Anyway, I think that's enough about performance. Point made. It is fast. So let's get back to the details of what I built here. It says it's an interpreter. It's not really an interpreter. It's more of a compiler, which is why I chomped up all 32K, is to write an optimizing compiler. And it's compiling to a bytecode, so there's a virtual machine as well sitting in that 32K. Most basics have what Python developers think of as a REPL environment, where you can sit in there and go print 1 plus 1 and it should do it for you, or print 4 times 5 plus 9, that sort of thing. I was looking for a language. I love languages, so I was looking for a language to develop, and the one that I really like is Forth. But you wouldn't get much traction with it because it's a bit cryptic for people to understand. So Basic is easier to understand. So what I did instead was I tried to build a Basic that is sort of reminiscent of Forth in that it encourages you to build small functions and to assemble your program from them. So do I have another example of that? Yeah, if we look at tic-tac-toe. So it shows the middle one. So let me make this slightly bigger. So if I take the top left corner, there we go. And I better take the bottom left corner. And I better take that one on the right. It's a draw, but it hasn't figured it out yet. I guess if I don't play either move, it can, but it's not going to. Anyway, draw detected, no winning moves left. Okay. So, and this input here, it shouldn't have taken, anyway. Let's have a look at the program. So if we look at funcs, you'll see what I mean about assembling it from multiple functions. So I can say something like draw board. Oops. If I put the second brace on, it'll work. Like that. So if you say list draw board, you get the idea. So you build up a program, and if you look at the whole thing, it's quite big. This entire program is quite large, but it's made of lots of little functions like that one. Can the player win? What's the best move? Check for winners, draw the board, clear the board, get a key, get a keystroke. And these are custom input routines using Peek to look at the 6502's keyboard buffer, input buffer from the serial port. So that one says, is there a key ready? And that one guesses the key. So you can make any old input function you like. And I've got another example where I can show you that too. Yeah, so I wanted to be able to build from small components and make it easy to build programs this way with functions. So it has functions rather than, those classic basics didn't have functions. They had line numbers and you had to sort of make up your own little areas of where your function was. So the original ones in the late 70s, early 80s had no functions, just line numbers. This has no line numbers. There is no goto. And that's done on purpose. A small footprint. So 32K isn't exactly small because some of those original basics were super tiny, like 8K. But they didn't have a file system built into that, and they didn't have a compiler and an optimizer built into that either. But I also have 32K, and I'm a one-man show, and this took me just 2 weeks to do instead of months and months. So I'm pretty happy with the fact that it's in 32K, and I've got 32K, so I might as well use it. It has functionality like Arduino style, GPIO type functionality, so that you can, so that you can. I've got, what do we got here? So I've got a program called Blink, right, which kind of does what you expect. And then if I Control C that and look at it, it's got, right pin, right. And the pin, I know the pin is number 0. I can say turn the light on and right to turn it off, like that. Oops. Oh, not off, false. Yeah, there you go. Yeah. So GPIO, it's got I2C. One of the reasons it needs I2C is to be able to read and write from that EEPROM. But I've got another I2C. I've got other I2C devices, like I've got a real-time clock. Let me show you what they are quickly. So I have a real-time clock that's I2C. Also old, like it's a 8-pin chip. And this is not so old. This is modern. One of these, but it sort of looks like Nixie tubes, But it's also I2C, and you can chain them together. So I'll do demos on those if there's interest on how to use I2C. Anyway, let's get back and carry on through. I'm just going to go through this fast. So like I said, it's got one numeric type, a 32-bit signed integer, which makes it really easier so you don't have to promote types, and it makes type checking really simple. So essentially you've got, 3 basic types? No, 4 basic types. So you've got this long, your numeric type, you've got a char. Oh, you've got strings as well. There's strings as well. They're immutable strings. And then there's a bit type. A bit type is like our Boolean type. So when something's expecting an expression like a while or an if, it wants a bit type. And then you can make arrays of all those types. So you can make bit arrays, or actually you can't make arrays of strings or longs. You can make arrays of bits and chars and shorter numerics. So bytes and words and ints. It does have a strict type safety. So you can't add a string to a number, for example. You can't, but yeah, it's kind of an interesting balance. So you can just declare a variable just by making v a variable like that. And by default, it's going to be an integer. So it's a long. You can see it tells you what it's actually a variant type. But I can assign a string to it like that. And then I can say print v, and I'm printing the string. It's a string. But I can't go do that because that's type mismatch, right? I can't do something like if the string or whatever. So it is strictly typed. So the only exception where you don't do variants is when you declare an array. So you can make, I can make a, let's do this first. So we've got 25K of RAM available. And if we make a bit array, and we call it ARR, and we say we're going to make it 20,000 elements, right? There we go. Have a look at it. They're all default to, everything's zero initialized to its default zero value, which is an empty string or false or zero or, yeah. Anyway, so I made a 20,000 element array, and now we look at our memory, and it barely used 2K, right? And that's because this is packed in bits, so that's 8 elements per byte in that array. So the arrays are super efficient. And you can also write them to disk. So the ones with the stars are executables, and these ones are data files. And you can read and write arrays. And if you read an array, it automatically dimensions it to fit whatever was in the file. So you can do data storage like that. Okay, let's fade back. Modern precedents, I'll talk about that in a second. Interactive functions, JIT compilation. I've spoken about the fact that it's a compiler, that it's got a peephole optimizer. You've got actual I2C commands. I'll show you those as well. And I've told you that you can import and export arrays. Okay, I'll put a link to this user manual and a link to where the binary is in the video. It's the only two things you really need. So this user manual has a user section and a reference section at the end. So let's just go through this quickly and we'll see if there's anything. Yeah, it does this multiple statements on a line with colons, as you'd expect. So variables are dynamically typed based on their initial value or based on what you set them to. You can do multiples with commas like that too, to initialize or not initialize them. You can have constants, which is kind of handy too, just a programming aid to know that you know things that you don't want to be able to modify, so you can't reassign to an existing constant like that. I mentioned arrays and how you can type them like this. Now, even though these are int and word, there is still only one numeric type in the system, a long, 32-bit long. So it's just an optimization for the storage of arrays. So you assign a long into this, or when you get the value out of this, it's a long, and the same with this. And you'll get a numeric overflow if it doesn't fit. So if you try and put something too big into here, or if you try and put something negative into a word or into a byte, there's a byte array as well. Okay, functions I've mentioned. It's kind of, yeah. I won't explain that now. Let's carry on. Yeah, you can. Arrays are one of the. It's the only type that you can only declare globally. Well, constants you can only declare globally as well, but you can pass them into functions as arguments. So you can say some array like that, and then add them up. Local variables, yeah, as you'd expect. See, the classic basics don't have this. They don't have scope. Everything's a global, and you're limited to 2-character variable names. So there's no such limit here, and you've got scope. And recursion works, with that scope. So this n's not the same as the next n in the recursive step. Whereas in classic basic, there wouldn't be functions and arguments. This wouldn't work. You wouldn't be able to do this in those classic basics. Yeah, the main program is begin and end, which is actually a hidden function. It's actually its internal name is $main, but and it has no arguments. But it's when you say run, it launches this function. Yeah. What else? Loops. You can imagine it's got a for loop. This is an implicit variable. Doesn't have to be. You can define it as a regular variable. It's got all the stuff you'd usually expect from for, but as I showed with the Knowles RetroLab demo, which is so damn fast, if I go list, so here we've got 2 nested loops. If it's if it's any variable, if these 2 are constant, and there's no step, you can optimize the hell out of this in terms of making this very, very fast. Yeah, it's got these built-in functions like millis and seconds. Millis, I get that from the Arduino world. But I think, can I do millis here? Not like that, but I can, because it's a function, not a statement, but I can say that, print millis, or I can say print seconds like that. Yeah, and that's the seconds since I last rebooted. So if I reboot and then I say print seconds, I get 4 seconds since I rebooted, which sounds about right. Okay, carrying on. While and when loops, do until loops, input and output. For input, I did have an input statement, but it's pretty useless. So I got rid of it for space reasons. And now I just craft my own input based on the circumstances. And that's by just using, like I said, peeking and poking to the serial buffer, which works really brilliantly. So I've got a couple of programs that work that way. Array storage I've mentioned, so you can export arrays and load arrays, import arrays, and it'll automatically size. So you can, when you start importing, you just say it's like 0 size, and then it'll just import whatever's in there and resize the array to however many you need. It returns the number of elements to there. The count, like the return value from import is the number of elements. Lots of data information about how this works. I've shown you how the pin mode and write and read work for, I didn't show you read, but I showed you write for when I was showing you blink. I2C. So it has an I2C library in it. And I can do a demo on that, which is pretty darn cool. So let's do that. So at the same time, I'll tell you about the file system. So the file system is actually a full-on fat file system, file allocation table. It's a 64K EEPROM, right? And it's got 256 times 256 byte sectors on it. And I've got a utility here called fat. And if I run that, it gives me a map of the file allocation system, a file allocation table, which is so each of these is a byte in the first sector. So the very first byte on the disk is the file allocation table itself, the thing we're looking at. The second byte has a D in it, and that's the first directory sector, because you can chain directory sectors together. So each directory sector can hold 16 files. If you've got more than 16, it'll add on another one, and it'll keep adding them on until you run out of disk space. And then these stars are sectors in files, and the E means it's the last sector in the file, the end of the chain and the chain link. And what this utility has done is for each file, it's shown us the chain link, the sector numbers that are occupied by the file. It's a diagnostic tool when I was working on the disk, on the file system. So the big files are made up of multiple sectors that are chained together into this linked list. And the linked list is the numbers in the file allocation table. If you've ever worked on a fat file system, you'll understand how this works. If you haven't, it doesn't really matter. But you can see you've got like 150 free sectors, and then there's 89 being used by files right now. There's your percentage free and all that. And you can see the file numbers, they're in order here. So the first file should be one sector. So let's have a look, because it's only 187 bytes, which is less than a sector. So yeah, the first file has only got one sector. Second file has got 1, 2, 3, 4, 5, 6, 7, 8 sectors. So what's 8 times 256? 2Ks, right? So let's look at our second file. Yeah, it's getting towards 2Ks. Okay. The cool part about this is that this utility that I loaded to do this is actually written in BASIC. So that's its functions. Let's look at its listing. This is the file allocation table diagnostic utility written in BASIC. And how does it work? The read sector uses I2C to read a sector from the disk. So just if you know how this disk works, and then it puts it into a buffer, which is a 256 byte buffer. There it is. So if we look at vars here, we should see the buffer. There's the buffer of the file allocation table sector. So pretty cool, and pretty reasonable program to write. Yeah. I was talking about input, like making your own input stuff, and I've got this little example here that I was playing with. So I can, with the arrow keys, I can drive this dot around the screen, and it's got borders. It's got like 80 by 25 or something. And this was me playing with the idea of using VT100 codes through this terminal emulator to see if you could make a game or something. Escape. And so if I look at this listing of the dot program, so it's got this main thing that goes up or down, left or right, depending on which key you press. But you've got a get key function. Is it key up, key down, etc.? And I think, does it even, oh, it just sits at the get key function. So how does the get key function work? Let's have a look. Get raw key, get key. So get key transforms them. So it transforms the key codes into lefts, rights, ups and downs, whatever the key codes were. And the key codes are going to be escape codes. There's an escape state because it's VT100 terminal. So it's getting escape codes and then it's converting escape A, B, C, that, 41 is A, into lefts and rights and ups and downs. So those are the VT100 codes for cursor keys. So it's converting them. But what's the raw key? Where to get that from? Well, while not key ready, well, what's key ready, right? So there you go. There's a bit expression, a Boolean expression. Key ready here is it's reading the input read pointer and the read pointer and the write pointer in the input buffer, and those are two constants that look into the 0 page of my 6502, and I've got a buffer at that address. And that's the serial buffer. And it's a circular buffer. It's Ben Eater's design. Well, I think it's his design. And if the in pointer is not the same as, if the read pointer is not the same as the write pointer, so that the serial chip writes it at the write pointer and you read at the read pointer, and the one chases the other. And if they're not the same, it means you've got a character to read. So it checks if they're not the same. If so, read one from the in pointer, which is like, that's how you read it. And then increment it. So take your pointer value, add 1, round it back to the value between, because it's a circular buffer between 0 and 255, and write it back in, poke there back again. So that's how the keys work. Anyway, so there you go. I2C demo, VT100 terminal demo, all in one. Let's go back and see what else I haven't mentioned yet. I mentioned storage management. Yeah, you've got a file system. You've got the usual functions. So it's got basically DOS. It's got, load, save, delete. It's got a format command. So I mean, you go format and gives you a big old warning, and then you say no, I don't want to format. Okay, I was going to talk about precedence as well. So I've got the full grammar here, and one of the things I have in the grammar is operator precedence. So again, like I said, I didn't want to just reinvent a classic basic when we've learned a little bit in the last 50 years. So one of the things classic basic did not do was have type safety. So and or, there was no difference between logical and bitwise. Whereas C kind of dominates in terms of language design. So every subsequent language, be it Java, JavaScript, C#, Rust, they all end up using these same operators and a very similar operator precedence level. So I decided to emulate that rather than classic basic. So I use the keywords and or a not for the logical operators, and I use the symbols for the bitwise operators. So bitwise not, bitwise or, and the bitwise and, which works. And the bitwise operator only works on the longs, and the logical operator only works on bit types. So you can't and or a char without converting it first, but you've got like built-in functions to convert a char to a number and back again. It's called CHR and ASC for ASCII. Numeric literals, yes. Again, modern. So use the C hex format to, if you want to put in a hex constant. You might have already noticed that in the source code. Same with this, with the escape codes for characters in strings. C style escape codes, because we're used to them and we know how they work, and here they are. The console commands, yes, clear everything out as new, list, run. Clear just resets variables. Yeah, there's this thing with basic. It's a good little demo. Let me demo it quickly. And this was the thing about, you can persist your environment. So if we have a var and it's a equals 10, and then we go begin, and we go print a, and then we go a equals a plus 10, and then we go print a again, and then end, right? So what do we expect to happen when we run? We expect to print a 10, add 10 to it, because right now the variable is, there's a lot of variables, but my a here is 10. So I expect it to print a 10 and then print a 20, right? So let's run it. There we go. We've got a 10 and a 20, right? And what's the variable now? It's 10. It's 20, okay? But what happens if I run it again, right? So if I run it again, it's currently 20, right? So you would expect that it would print 20 and then 30, but it's not going to. Oh, not print, run. It prints 10, 20 again and again, right? And that is a feature of BASIC. It takes those initial values and reinitializes when it runs again. And it's an important feature of a language. So when you run, you get expected behavior from your globals. So, resetting your arrays, resetting your global variables every time you run. And it would have been easy not to do that. So it's harder to do that, but it's an important feature to implement. Okay, what else we got? Variables, functions. Yes, you can forget a variable or you can get rid of, delete a specific functional variable. The disk commands are save, load, directory, delete, and format. You've seen those. Buy has not much purpose because you basically hang your machine, say goodbye. It's got diagnostic tools when I'm running in debug mode, like I can look at heap and dump, and it's got a tron and trough, trace on and trace off to trace execution. But they don't fit into 32K. I've got to run a bigger ROM to do my debugging. The data types I've spoken about. Yeah, strings are immutable, so you can't modify an existing string, but it's amazing. I mean, all the software you've seen up to now has used immutable strings. It's not a thing. It makes it much easier to implement if you can't modify a string once it already exists. I mean, you can assign a new value to a string, and then it destroys the old one and makes a new immutable string. But you can't change like a specific character in the string. But you could. I've simulated it using arrays of chars. So you make your own little string manager in BASIC. Anyway, array types, operators, we've mentioned. What else? I think we've gone through enough here. Do I have another demo that you haven't seen? Peek and poke, I squared C. Oh, did it have built-in functions? Yeah. So built-in functions like millis and that. Built-in functions like length, like absolute. There's a random number so that you can make... it's handy for games. CHR and ASC for converting characters to numbers and numbers to characters. The GPI opens, I squared C, error messages, lots of error messages, yeah. Oh, it's got an auto-exec. So if you save a file with the name auto-exec, just like DOS, next time you reboot, it launches that file, starts into that file. Thankfully, Control-C always works, and the NMI button acts as a second Control-C. I can demo that quickly. So if we run Mandelbrot, so instead of pressing the Control-C key, I just press that and I get a break. So it's a non-maskable interrupt. So there's no way your auto-exec will ever destroy your system, will ever, brick your system, because that NMI is impossible to stop. Yeah. And it's also super efficient, so you don't have to poll for it. Yeah, so what else we got? All the rest is, a couple of demo. There's a lot in this. Anyway, I think that's enough of a demo. I've spent enough time on this. It's about a half-an-hour video, which is quite long for me. So I think I shall just end on that Mandelbrot again. And this is Gordon Hedison's Mandelbrot from his Tiny Basic. Only in my system, if you look at his benchmarks, he's got timings of them on his website, on his blog, is how fast they are. And obviously this is like a hell of a lot faster than any other example out there, irrespective of the fact that I'm running at 8 megahertz. Anyway, thank you for watching. There's a whole playlist on how you build this machine and get one for yourself. And if you've got questions about how to install this, because I'm going to have the link to the binary that you put onto the ROM, and have a link to the manual in the video, and that's all you need. I haven't documented the settings for my terminal here, so I haven't documented these very well yet. I can give a quick rundown of them. This is it. So I'm running at 56700 board. I'm running 8 data bits, 1 stop bit, no parity. And it's important that you switch flow control to X on, X off, because when I first built this board, I didn't hook up hardware flow control, so I can't use CTS, RTS, CTS. But flow control, it's important because the easiest way to get a program onto this device is to paste it into the console. Just paste the text of your program into the console, and that's how you get it there. But if it pastes too quickly from a desktop machine, so you need X on, X off so that it can tell the host to slow down and stop swamping it with bytes. So those are the most important settings, I guess, for setting up serial. So 56700 board, 8 data bits, 1 stop bit, no parity, X on, X off for flow control. Yeah. Anyway, I look forward to the comments and the feedback and questions about how to use it or how to install it. I'm happy to answer all those. And then I think I'll do a few more videos. Like I'll do another one. I'll do another video to demonstrate the real-time clock. We can build a clock. And I'll do another one to demonstrate using these displays, or maybe it's not very retro, but Anders Nielsen's board uses this little OLED display as well. It's also I2C, so we can hook it up as well to our this is our parallel port here, and some of the pins on our parallel port are bit banged I2C. Yeah. Very good. Thank you for watching. I'll catch you in the next one.